So thanks for joining this session. What does reliability mean to you? My name is Sami Kassimäki and I'm a product manager at Tuxera. Tuxera is a world-leading file systems and networking technology company with over 30 years of experience in the embedded industry, file systems and storage management software. Today, we'll be talking about reliability and how storage can help with preventing field failures. So why are we talking about it? Reliability is one of the most important factors distinguishing leading embedded products from their also-ran competitor. However, it's a promise that nearly everyone makes, but the definition of reliability and importance can vary. Embedded devices operate in conditions where sudden power interruptions and other hazards can occur at any time. When these devices fail in the field, the consequences can be significant and costly. Now, in this session, we discuss what reliability means to you and how the storage choices can help or hinder you in providing the reliability your customers need. In this presentation, we'll start with a brief overview of some of the consequences if reliability isn't achieved. Then we'll drill down a bit into different levels of reliability and understanding what they mean. And finally, we'll cover some techniques to mitigate sources of failures. We'll cover concerns related to flash media, programming techniques for avoiding common pitfalls, and the file systems and what file systems can do to provide greater protection against failures. So first, let's take a look what consequences of what could happen when reliability fails. Benjamin Franklin provided an example of consequences of failure in Poor Richard's Almanac back in the 1700s. For one of a nail, a shoe was lost, and for one of the shoe, a horse was lost. For one of a horse, a rider was lost. For one of a rider, a battle was lost. For a battle, the kingdom was lost, and all for the want of a shoe nail. Now, in a modern world, when reliability fails, the consequences can vary from merely annoying to catastrophic. A hardware failure can lead to engine failure, and the system integrity issues can lead to infamous blue screen of death. And data integrity can lead to consequences from lost photos from your summer vacation or to a cascade of bad decisions in the data-driven systems. Now, reliability matters because the field failures are costly. In addition to a direct replacement cost, dealing with the failure in the field drains resources from other places, which is usually from product development. Customers and company management typically want an explanation of how and why the failure occurred, and that is root cause analysis. Along with the fix, of course, for the failure and plan how to make sure that it doesn't happen again. Now, from developer perspective, the work required to respond to a field failure represents a distraction from the work that they're developing for the new generation of the products. And when companies are struggling to innovate or die, distractions posed by the root cause analysis and the potential redesign can make a difference between the success and the lost kingdom. Now, user experience is often considered when a user and performance are considered. However, reliability issues with the devices can lead to poor user experience and reputation damage. Now more than ever, reputation matters, and bad experience leads to bad reviews, which can close doors for growth. With embedded devices making their way into more complex and interconnected systems, creating the data powering new business models, the losing of the missing critical data could be catastrophic. Imagine, for example, if the power meter would lose all its billing data. Now, when you consider reliability, one question you should always ask yourself is, how much the data generated by the system means to you? But maybe even more importantly, how much the data means to your customers. So let's move next to discuss different levels of reliability. So what does reliability mean to you? As mentioned earlier, the definition and importance of reliability can vary significantly. We've divided reliability in the embedded systems in 3 categories, and these are from the storage stack perspective. With these definitions, we want to discuss different levels of reliability, which are crucial for the overall reliability of the embedded systems. First and most obvious layer of reliability is, of course, hardware reliability. This means that the device powers on. Once that is achieved, the next link in the chain of the system integrity means that the system is able to boot up correctly. And finally, when you have important data on your system and you want it to be there when you need it, that's called data integrity. So let's take a look in more detail about the different levels. As said, reliable hardware is basis for overall reliability, and in broad terms, it can be defined as does the device power on? Now, demonstrating this level of reliability is perhaps the most simple, and perhaps for some systems, this level of reliability is enough. For example, for early embedded devices, those turned off, on, and that was enough. However, in the modern complex systems, power light alone may not be a definitive indication that all is well with the hardware. For example, a storage device, they are not created equal. Corruption can happen on a storage hardware that isn't obvious at first glance, and it can be fatal for the device. Similarly, a memory corruption or a bus corruption can also occur. Most systems have hardware checkup at startup, but few have storage health check, as it can be a time-consuming event. For your embedded data, if a failure occurs at hardware level, if a storage corruption or a memory corruption occurs, you can lose all your data. And making the right storage choice can help mitigate these issues. With the increasing of complexity of the systems and more data being generated by the systems, it's important to consider the whole lifetime of the system. Flash devices have limited lifetime, and the amount that can be written to the device varies based on the workload. With hardware reliability, the important question to ask is, the device doesn't power on, what are the consequences to you and your company, and how can you resolve that? And most importantly, is only a hardware level of reliability enough for your customers? Second level of reliability we are talking about is system integrity, as in does the device boot up? As mentioned, the embedded devices operate in conditions where power interruptions are commonplace. Now, in order for the device to boot up, it needs to be able to read the bootloader and other programs for the storage media. Assuming the storage media passed the hardware check, system integrity requires that the metadata of the file system is readable and free of corruption that can happen due to power failure or unplugged storage. Unfortunately, some of the often used file systems for embedded use cases, such as basic FAT, are not able to provide this type of a guarantee. When the devices that feature this high system integrity are designed to start up even after an unexpected power loss or a system crash, meaning that the media won't get corrupted even when the write operations of the media are interrupted. At this level, the file system either ensures metadata consistency or will resolve any inconsistencies and leave the system in a functional state. Given that the embedded devices operate in conditions where power interruptions are common, the important question you should ask, how have you prepared your devices for the power interruptions? The third level of reliability is data integrity. This means that data read back is what the data that was written, and nothing is missing or altered. Ideally, data is always in a consistent state, and a known good state is never overwritten. This means that there are no partial files or corrupted media. This level of reliability is crucial, for example, in the medical field, where regulations dictate that when you save settings, they must always be stored correctly, and even in the event of a power loss or in-flight. And another example is an in-flight recorder where crucial crash data needs to be fully recoverable. Now, when the power is lost or a system crashes, the data that's not yet committed to the media is subject to a loss. And crucial part is about understanding what data is or what isn't committed to the media in order to ensure the data integrity of the device. The challenge of uncommitted data can exist both in the file system and the media, and both can have uncommitted data in the caches or the buffers. And controlling how much and what data is at risk of being lost is the goal in order to achieve the expected level of data integrity. So with these definitions in mind, let's move on to discussion how we can design our systems for the appropriate level of reliability. I'll be covering 3 different areas: hardware, programming techniques, and file systems, and discuss considerations from the developer perspective. The main goal is to discuss how you can provide the highest reliability for your storage stack and your system. From the hardware point of view, we'll focus on the concerns for the storage hardware, including long-term reliability with flash, as well as the importance of testing. We'll then cover a few programming techniques that can be used to increase system reliability. And finally, we're going to talk about how file systems can provide additional level of reliability while reducing complexity of the system. From the storage hardware perspective, we'll discuss flash media and considerations for long-term reliability. So software can go a long way for providing system integrity, but software is only as reliable as the hardware it's running on. The flash media provides some unique challenges with regard for the customary expectations of Moore's law. The hardware is not always improving in every aspect. Now, by design, flash memory has limited lifetime, and based on the number of write cycles it can endure. If maximum number of write cycles is reached, it can lead to unreliable data, or in worst case, the whole system can fail. Embedded devices, by nature, can have extended lifetime requirements for 10, 20 years, or even more. At the same time, previously read-only use cases have become more write-intensive. So why is this a concern for a developer? In many organizations, hardware and software is becoming more separated functions, and that can lead to disconnect. If a hardware is used beyond its capabilities, data corruption or a system failure can lead to reputation damage. An example of this can be found in a very recent history where a certain electric car manufacturer had to recall more than 100,000 cars to replace an eMMC device, which is not an easy feat. While software-defined architectures are great in general, it poses challenges for the development. How can I ensure that my device will last for this long? From the developer perspective, one of the often overlooked considerations for flash media is write amplification. Now, write amplification is an undesirable phenomenon that results when actual amount of physical information written to the device is more than the logical amount intended by the application. This can lead to early flash memory wear out and can cause critical issues leading to even system failure, as well as cause performance issues in the long run. Let's take a look at how write amplification happens from application to the storage media. So write amplification starts from the applications, where applications first writes the data to a file system. The file system must add some amount of metadata in order to be able to retrieve the data in the future. Now, depending on the file system, this can be smaller or larger, but there's some additional cost there. When this data is then transferred to the flash media, it's written and stored across a number of memory units or plugs. Now, due to the nature of the memory, over its lifetime, data might be moved around, and that's due to garbage collection and wear leveling on the device. That's inherent for the design for the flash devices. Now, when considering writes, usually a 4 kilobyte is the smallest amount that can be written to the device at once. If application is writing smaller chunks of data, the data is usually cached in order to write more at once. However, if the small writes are forced to the disk, this can create additional overhead. One extreme case of write amplification was found on Android-based systems, where SQLite is used heavily. Now, SQLite uses frequent F-sync calls, where we've measured write amplification of over 100. This would mean that if 1 megabyte was intended to be written by the device or by the application, on a device level, that could be as much as 100 megabytes. So as flash technology is moving forward with incredible speed, it brings performance and reliability challenges to device manufacturers. Now, shortcomings in product selection can result in choosing more expensive part for just in case, or you can end up with something that seemed okay with limited testing, but ends up failing in the field, leading to product recall expenses or other bad outcomes. Now, as a part of testing for embedded design, a flash lifetime should be validated. Many of today's embedded devices use managed flash, such as eMMC or UFS. Whilst these devices are based on standards, they handle the things differently inside. This means that using the same workload on a different storage devices can lead to highly varying lifetimes. So, working within the storage stack, we have provided comparative analysis for our customers. Here is an example of a workload that represents an automotive infotainment system with all its applications. While the amount intended to be written on the device is essentially the same. On one device, we measured write amplification of 1.9, but on the other device, which was based on the same standard, we measured write amplification of 4.2. Now, in our testing, this was the difference between 10 and 20 years of life. To prevent field failures and ensure system integrity, extensive is then needed. This testing can be done in real world, using real world workloads in simulations. As discussed, the file system and flash device are both key components for the lifetime. And what's more, testing those components and ensuring that they work well together is crucial for the reliability of the whole system. Now, when testing the flash lifetime, it's important to validate to higher standards and even exceed your customer expectations. Even the unusual cases that will likely occur in the field should be extensively tested in order to guarantee the reliability in real-world use. Let's next take a look into programming techniques, which can increase the reliability of your system. We'll take a look into 3 main programming techniques that are used for the reliability. First, we'll take a look into read-only partitions and files. Second, we'll talk about flushing and syncing. And last thing we'll discuss is direct I/O. So one trick used by the developers is to put the system files on a separate partition, or in some cases, even on a separate media. This can help preventing file system corruption and increasing system integrity, especially when the partition isn't written to. So it is somewhat free from corruption. Another technique is to mark files as read-only with the read-only attribute. This can help increasing the reliability as the data on the file cannot be changed. However, this only keeps the file system from touching this file. Now, media failures can overwhelm both the attributes and partitions and can corrupt files. And this is a particular problem with NAND flash media, where the managed flash devices are doing background operations for garbage collection and wear leveling all the time. Now, other commonly used method for increasing system integrity is flushing or fsync command. This command transfers all modified data to permanent storage, writing through or flushing the disk caches, while syncing the contents on the media can help with reliability to certain downsides. Fsync is used by some applications very frequently, as we've discussed, and this is often done to ensure correct ordering of the data. However, this also means that the data is written to the permanent storage. So here we can see a stochastic test which performs a standardized set of random operations such as reading, writing, creating files, and removing folders, etc. This test was run on fat file system, and as we can see, there's a huge performance penalty in using very frequent fsyncs for increasing reliability. Especially if fsync is called after a small update, it can create significant overhead. As we discussed, if the smallest unit to be written is 4 kilobytes, if we write less than that, the rest will be additional overhead. On a Linux file system, there's a particular persistent myth that opening a file with ODirect is all that is required for data to be reliably stored in the media. Now, ODirect bypasses the Linux kernel caches, but it also takes into account only the data. Now, this means that to sync metadata, fsync is still needed. And working on the speed of the media is fairly inflexible. If the data is captured faster than the speed of the media, then caching is used as well. In short, using ODirect usually decreases performance, but does not always commit to the disk. So here is the same stochastic test that we performed in the last slide. And this is a comparison of using ODirect and not using it. As we can see here, there's a performance penalty of using ODirect. However, when fsync is factored in, either with using ODirect or not, the performance can significantly or can drop significantly below the speed of the media. As an addition, using buffering allows for pre-processing of the data, such as compression or encryption. And with today's focus on security, this should be considered when selecting reliability methods for your systems. So we've discussed several programming techniques that can help to increase reliability. As discussed, programming techniques can help with reliability of the system, but they also can increase complexity, and they must also be included in the coding standards when writing the applications. So next, let's take a look into reliability methods that file systems can provide, while also possibly helping with the complexity of these systems. So first and foremost, not all file systems are created equal. One of the most often used file system formats in embedded systems is FAT, which is short for File Allocation Table. Now, this originated in the desktop environment and has been around since 1970s. It's widely adopted, largely due to its simplicity and interoperability with PC world. Now, while commonly in use, it's a less than perfect solution for the embedded systems. This is largely because FAT was originally developed for the desktop environment where hazards such as power interruptions are a rare occurrence. And this can lead to problems with embedded devices where the power disruptions are common. For example, interrupting a write in the middle could cause a catastrophic corruption on a fat file system. In a worst case, causing the whole partition to be lost or irretrievable and potentially even preventing the system from booting back up. Now, beyond FAT, there's other file systems that can provide additional mechanisms for increased reliability. Next, we'll take a look into two different file system types, journaling and transactional file systems. So going beyond FAT file system, journaling is the most common method for increasing system integrity. And that's used by many open source file systems. File systems that use journaling tracks the metadata changes in an additional reserved location called the journal. When recovering from an unexpected interruption, journaling file system walks through the structures on the media to decide which of the files are valid and which are not. After that, an FSCK tool is used to recover any lost space and correct any errors if there are found. Now, many of Linux file systems use journaling, including X4, BTRFS, Net2FS. The downside of journaling is the additional overhead that it causes. With journaling file systems, the metadata changes are written twice, once to the journal and once to the media. Now, in addition, after an ungraceful shutdown, replaying the journal can lead to inconsistent mount times, especially when booting up after a power loss. An additional note, journaling can also be used to improve data integrity. However, when journaling is used, it can have significant overhead, as all the changes are written in the journal and then to the media. And this usually leads to significantly reduced overall performance. And unless data journaling is used, while metadata journal can help restore the system to a functional state, the data on the media might not be exactly what's expected. So we'll shortly take a look how journaling works on a block level view. But first, let's take a look into transactional file systems. Transactional file systems are developed with embedded systems on mind. Transactional file systems such as Tuxera's Reliance family can mitigate performance issues caused by the journaling and provide both system and data integrity. One of the ways this is achieved on a transactional file system is by not overwriting the data on the media, thus preserving a known good state. Transactional file systems write changes only once to the media, to the working state. After committing the changes to the disk, a transaction point is issued and a meta route is updated and the state is now preserved. We'll shortly take a look how this looks on a block level compared to the journaling file system. After unexpected power loss or a system failure, this type of file systems mount quite quickly. It merely must determine the proper media state by reading the two meta routes. And this means that there is no need for a check or a cleanup on a boots up time. Compared to a FAT file system, where a check disk might be able to fix lost clusters or cross-linked files, these similar issues cannot happen on a transactional file system. So, as we've discussed, data at risk can be managed with mount settings and flush and sync commands, and of course, the other designs of the software and hardware. However, in many designs, this control can be directly opposed to the raw performance of the system. And for this reason, transactional file systems provide an additional runtime API to control the data at risk settings through a special API. So here's a block level comparison on media layout comparing journaling and transactional file systems. Both file systems have a master block here in the red, which is crucial for booting up the system, and it's rarely written too. Now, as mentioned, in journaling file systems, changes to the metadata are written twice, once to the journal and once to the media. The user or file data is written only once. As we've discussed, most also have the option for data journaling, but since they write everything twice, they're quite slow and most customers don't want that. On the other hand, the transactional file system has two meta routes, which is where the reliability comes from. More about those in a bit, but also this means that the metadata and user data are written only once. And you can see also here that there's less overhead and more free space available on the device. So here's a rough example of a file changes on a journaling file system. Three basic operations are delete, modify, and create a file. One key difference in journaling and transactional file systems is that on a journaling file system, the files are modified in place unless certain programming techniques are used to do that in a different way. The metadata is not modified in place, and the new data is written to the journal first. Now, when a power is lost in the middle of an operation, the state of the media is unknown. And when mounted, the media works through the journal and compares the state of the media. And this way, the metadata is not corrupted, meeting the system integrity criteria the system will put up, but the file data might be overwritten in place, or depending when the power is lost, it can be in old state, new state, or in the middle, which means that it can be essentially corrupt. Now, here are the same three operations in transactional file systems: delete, modify, and create a file. In transactional file systems, the operations happen first, and then a meta root is updated. Now, there is no overwriting of the data, so all modifications are done to the free space. So on success, the media is in the new state, and as we would expect, if the power was lost before the meta root update was complete, the media will mount to the original state, so nothing will be changed. And this is one of the reasons why transactional file systems have fast mount times. It only needs to read the two meta roots to figure out which one of them is current. Not overwriting the data means that we can check both boxes, providing the system integrity as well as the user data integrity. As mentioned earlier, developers can customize the conditions under which transaction points occur, and they can even change them at runtime. One of the example of that is a system file update. If the space allows, a complete update of the system could be even done, and on success, the transaction point could be committed. However, if an error occurs, a system could automatically revert to the previous state. So let's then take a look into how you can test your system to ensure the level of reliability your customers expect. And taking into account as well that the best testing meets both the needs of the strictest users and the goals of stressing the system in the best way. When testing file systems, it's important to keep in mind that the performance of the file system is always use case specific. Hence, performance testing should be done in relation to how the device will be used on the field. Power interruptions are commonplace for embedded devices. And that said, power interruption testing should be a key part of testing for the embedded applications. Effective testing should show that there's no media corruption due to power failure or unplugged storage. And keeping in mind that interruptions during writes will demonstrate the most failures and accurately reflect also the stress that the devices are under and in the field. To meet the strictest requirements for performance and reliability, corner cases should also be tested, especially performance-wise, what happens when the device is nearly full. Besides the potential performance implications, this full situation generates more writes as garbage is collected, and that leads to more possibilities for vulnerabilities. Now, how about if there's 100 files on a directory? Does the system latency increase noticeably when after the first 100 files? Both of these situations can lead to large write error windows and can lead to a potential failure. As we discussed before, another stressor in the system is system update. This is a situation that is especially important to test thoroughly, especially when power interruptions may occur. Atomic writes here can be a major factor, which allows the device to recover from a failed update. When testing a file system, it's important to remember that the real testing of reliability is more than just a requirement. It also leads to long-term success of the embedded design. The reliability mechanisms that are used can also impact the mount time of the device the most directly. When analyzing the performance on a power interruption testing, a mount time should be considered as it directly links to user experience of today's devices. Now, here we can see three types of tests where we're comparing a transactional file system to journaling file systems, FGFS and X4. We have fresh file system with no writes having been done, stochastic test that we discussed before, and FSIO test that performs a standard set of writes followed by a clean shutdown. The impact is considerably more with power interruptions in the mid-test. Here's the same stochastic test that baffles the X4, causing the average mount time to stretch over 2 seconds. This is caused by the journal replay on the volume, and even though FGFS is fairly stable in the reaction for both of these tests, the average mount time is more than a second, which is considerably more than the mount time of the transactional file system. With the transactional file system, the mount time is the same as with the normal dismount, and especially with today's more complex systems where boot up times can increase significantly, mount time of a file system is a key consideration for user experience. So we've gone over definitions of reliability and ways we can improve it. So let's take a quick recap what we discussed. So reliability means one of the most important factors that distinguishes leading embedded products from their also and competitors. Anticipating and preventing field failures enable the market leaders to invest in innovation rather than being bogged down by costly resource training, diagnosis and repair, and redesign. Today, data integrity is a strict requirement in other industries, such as medical, but not in others. However, as embedded devices are entrusted with more data all the time, the need for a fail-proof data storage is emerging as more relevant across the board. The correct testing can enable you with deeply understanding the reliability of your devices and with the precision unique to your use case. Programming techniques can help with increasing reliability, but these can also add complexity to the application layer and may not be universally adapted by all application developers. Therefore, a file system with additional mechanisms for reliability can help with dealing with the applications from multiple sources, as well as maintain the overall performance for the whole lifetime. And with that, thank you for joining and hope you've enjoyed this session. If you're interested in learning more, we have a white paper available on this subject on our website, tuxera.com.
Thanks, Sami. Lots of great info in there. I have a couple questions for you. Is there a recommended combination of like file system type, sync method, etc., for a read-only operating system in 2021?
The read-only use cases are a bit easier on the device, but it's crucial to keep in mind the reliability of the system in terms of having the read-only partition only on one device.
Okay. So using like the latest techniques and the stuff that you talked about in your talk, how long can a person expect an average flash chip to perform well without any degradation under moderate usage? And how much does the file system being read, write, or read only affect that?
Flash lifetime is always use case specific. So it depends on multiple factors, such as how much is written to the device. And we can capacity of the device, write intensity of the application, as well as environmental aspects. So it's always important to validate for your own use case.